Recording. Now I have to be nice. Sorry, guys. It's just a daggum challenge. Is it just me? Or, I don't know. Man. The other class is doing better. Yeah. All right, we don't need that picture. All right, let me see. What was I going to do? Good Lord, I can't remember anything now. Okay, so I did record a little bit of power factor stuff, and you should watch that, a little bit more explanation. But I have an example here that I kind of like. I mean, it's not super, but I am going to give you a homework assignment one of these days where you get to play around with some of this. Okay, so you got everything up? Hopefully everybody can hear me. All right, disaster avoided. We'll see. I've got 2 bars on my cell phone. I mean, I was able to get 3 bars earlier in the first class, but anyway, hopefully that's good enough to do the Zoom recording. All right, so this is just a little example, and I can email this out to you. You can take notes if you want to, but it goes through some of the calculations. So I just made up a monthly bill, and when you look at the rates, you got to realize this was done a few years ago because rates have gone up significantly. But anyway, let's say that we own this little plant, and this month we use 315,500 kilowatt hours. So that's electrical energy. And our actual metered demand peak for the month, which is typically a 30-minute, it can be a 15 or 30-minute average, but it's considered kind of an instantaneous peak. They average it out so that, you know, if you have large motors in a facility, when they start, the inrush current is like 6 to 8 times the normal running current. Okay, but it only lasts for a couple seconds. It depends on the inertia of the load, but it doesn't take long. And so if you did an actual instantaneous peak, that inrush current would help to set a peak. But if you average everything over 15 or 30 minutes and you kind of smooth out those individual spikes that only last for a very short duration. So it's to whoever's paying the bill, is to their benefit to have as large an averaging period as possible. Of course, the utilities always want to shrink it, and the consumers always want to, or the companies always want to stretch it. And then they have to go before the Public Service Commission and make an argument, and the Public Service Commissions make a decision on what they think is reasonable for both sides. So that's kind of how that runs. But so the 683 is the actual real kW power peak for the month. The meter also recorded apparent power at 882.4. And of course, we know power factor is what, just the ratio of those two on the power triangle, the actual divided by the apparent. And the threshold for penalty is 95%. So if this power factor is below 95%, then they're going to pay extra money to the utility. And I guarantee you it is, because I made this up. And you see the rates. This is a GSA 3 rate. It's, well, supposed to be between 1,000 and 5,000 kW demand, but I kind of violated that. But anyway, that could be their contract demand for sure. But anyway, so the customer charge back in the day was $10.94. They get to pay that just for the privilege of being a customer. And then on the demand, the first 0 through 1,000 kW was $10.91. And so they didn't go above that. So that's, and then the additional, it got more expensive. But that 1267 rate won't come into play here in this. And then on the energy side, it's pretty simple. All kilowatt hours are what, 4.269 cents per kilowatt hour. So pretty easy. Okay, so we want to calculate all of this stuff. the electrical energy charge, the power factor, demand, charge, kVARs of capacitors needed to correct power factor to 95%. Assuming that to purchase capacitors cost about $75 a kVAR, what's the cost of the project to correct power factor to 95%? And reduction in electrical current. Oh, here we go. Unstable again. EM. And my cell phone was not even very good. Let's hope it doesn't die. If it dies out there, I'm sorry. I've got a request into IT, and they're going to add some more Wi-Fi equipment to this room. They didn't think they'd get it this by the end of the week, maybe next week. So I think this problem is eventually going to go away, but I'm not sure when. And what's the reduction in electrical current from the capacitor location back to the power plant? Because that's where you get the benefit, is from the application of the capacitors back to the plant, the generating plant. Okay, well, we'll start out really easy. The electrical energy charge, it's 315,500 kilowatt hours times the rate. So that comes out $13,469. If my arithmetic's any good. I think it is. I hope it is. Okay, so this is kind of where the rubber meets the road. We draw the old power factor triangle. And so up here on top, and let me see, I need to get my arrow turned on here so it doesn't disappear on me. Always forget to do that. Okay, so the real power, the kW, put up here is like the cosine side of the angle. And then the apparent power is the hypotenuse. And then the reactive power, the kVAR, is the opposite side from the angle, or the sine side of the triangle. Well, so we're given these two numbers, and golly, I mean, those kids in junior high school can use Pythagoras Theorem right on their calculator, so I trust you can too. You know, I got confidence in you guys. So, you know, if you take 882.4, square it, and subtract 683, square it, and then take the square root of it, my fond hope is that that equals about 558.7 kVAR. So that's just Pythagoras Theorem for a right triangle. And that's what they're built on, okay? That's what they did for the month. Now, let's see what the power factor is. It's nothing but kW divided by kVA. So that's 683 divided by 882.4. Well, that comes out 0.774, or 77.4%. Not so good when you're held to, if 95% is passing the test and you made 77.4, mom and dad are going to be disappointed, right? I mean, you know, so the plant failed the power factor test this month. And the utility company, they're smiling because they go, all right, we get more money. We're gonna zing you for this. And if you want to know what that angle is in there, you can take the inverse cosine of 0.774, and it comes out 39.3 degrees. Not that it really matters much, but I guess if you want to draw the triangle accurately, you could do that, which I did not care to do. Okay, so this slide just says we are paid a power factor penalty. Everything else is the same. So, all right. So now there's different ways, different rate structures will have slightly different calculations, but they all kind of go back to the power triangle. It's just how the rate structure is written. So one way to do it is they say, okay, your real power is 683, but see, that's going to be the same no matter what the power factor is. So the number that changes is the apparent power. And they say, okay, so 95% is your threshold. So how about this, big guy? We'll take, did I go one too far? Yeah, we'll just take that kVA and take 95% of it. And the calculation is below. That's 883.3 kVA but they're going to treat that as kW, and they're going to bill you based on 883.3 kW on your demand charge, instead of, it could have been 683 if your power factor was 0.95 or above. So if you, yeah, I mean, so in other words, back up here, we see that, you know, this, the 882.4 times the 0.95 is going to be 883.3 times the rate is $9,146. Well, what could it have been? Let's say you ran a 0.96. See, you can't get out of 683, even if you run one perfect. You can't get out of 683. You're going to pay for 683. But if your power factor is below 0.95, you're going to pay more somehow or the other, okay? So, well, let's see, how low could your demand charge have been? Well, 683 times the rate is 74.52. So the difference in these two numbers is your penalty. So you're paying an extra almost $1,700 this month in demand charge because your power factor was low. And that's how they're going to ding you. The other small piece that you will also pay your line losses, your I²R losses, because that extra current's flowing through your wires, it's going to heat up a little bit more. That's probably on the order of, I don't know, 0.5%. I mean, it's small, but it's there. This presentation, this is a bigger presentation. I'll show you. I'll send this one to you too. What the hell? There is a slide or two in here that does a little calculation to estimate that extra little bit, but I didn't throw it in this example, I don't think. Okay, so is everybody clear about how we're being penalized here in this rate structure? Okay, great. Okay, so let's correct this, okay? So the big outside triangle is the one we've already worked with, okay? It's got the apparent power, the hypotenuse is 882.4. The long sine side over here, this entire side is 558.7. And this is the 683, so that's the real power. So that's the same triangle we had. But, so if we start putting in capacitors, we can shrink this side. Say the capacitor is the anti-inductor. And that's enough for a mechanical engineer to know, well, you know, what the heck. You know, you can go talk to those double E's down there if you want to know more about it, you know. But anyway, this is the practical stuff out there in the real world that people have to pay for. So the way we can calculate this is, well, okay, so if my power factor was right on 95, says power factor is kW over kVA, let me just solve for what the kVA would be. So if I take the 683 divided by 0.95, in this smaller triangle right here that has a power factor of 0.95, this hypotenuse would be 718.9. So see, this side right here would be 718.9. So that's just our desired power factor divided into our real kW. And the real kW is like solid. It's anchored. It ain't going anywhere for that month, okay? So then we have a smaller triangle in here. Well, we're back playing Pythagoras' game, okay? So then we take 718.9 squared minus 683 squared square root, and we get 224.3. So that means that we are, come on now, honey. Don't you be doing this to me. Behave. It's like raising children, you know. Behave, dadgummit. Try to get my dog to behave me. Okay, so another way of saying it is, if this is your real power, the power company will allow you 224.3 kVAR of reactive power before they start penalizing you, okay? So this is what we did, 558.7 if I subtract 224.3 from it, I get 334.4 kVAR of capacitors, will move me from this triangle to this triangle, which just gets me out of penalty. Okay, and the payback in investing in this is really mostly to just get out of penalty. The only thing beyond that that really saves big money is if you need the capacity in your MCC, your motor control centers, because those are like the power feeds come into the MCCs, and the MCCs feed, you know, a bunch of different loads out there. They're like in the electrical rooms of the plant. A big plant might have 5 or 10 MCCs. So the big power feed comes in, and then each MCC gets fed separately. And then from the MCCs, it goes out to the loads. Well, we might have MCC number 5 over here, and man, I got to add another 50 horsepower pump. I got to have it. And you go in there and say, man, this thing is pegged. No more capacity. Say it's a 2,000 amp MCC, and you put the meters on it, and it's pulling 1972. And you're going, hey guys, we can't hang another 50 or 100 horse motor on this thing. Well, so then what you can do is go out and measure with a good power meter. You can measure the power factor. You just clip it on each motor, and you go, oh man, this motor is running 75% power factor. This motor is running 60% power factor. This motor is running this. So you can go to the individual motors and put capacitors on. And then the current reduction goes from the capacitor all the back through the MCC, all the way back to the power company. And all of a sudden, hey boss, we got to spend $2,500 on little capacitors, but all of a sudden we don't have to spend $50,000 to expand the capacity of the MCC. And you get patted on the back, and the guy says, hey, I'm going to remember you at bonus time, you know? I mean, so that's the other motivation other than to avoid the penalty. And that, it doesn't come up every day, but it's not uncommon to need to unload an MCC. Okay, I think we got everything on there. Okay, so now, look guys, when you get out there in the real world, don't call up a vendor and say, hey, I need to buy a 334.4 kVAR capacitor bank. That's like going to the Chevy place and saying, I want a 372.5 horsepower engine. The guy's going to look at you like, you're an idiot. You don't know nothing, boy. You are not dry behind the ears. You know, you got to look at this, and you're going to round up. You're going to go 350, you're going to go 400. You know, and the other thing you can do is you can put a recording meter on the plant or whatever and see, because this is going to vary over time. It's not stationary. You know, and because what you get into on the capacitors, you can buy, say you buy a 400 capacitor bank or a 350, you can buy it in stages with automatic switching. So, you know, now the cheap way would be to buy three. If this thing was just stable like this all the time, the cheap thing to do is buy 350, just static, put it in there, but you always get that correction. So if this kVAR goes down, you can drive this thing past 1, and oh yes, they'll penalize you for leading power factor as well as lagging, not as much. Even though it helps them, they will still penalize you for it. I've seen bills where they get penalized for leading and lagging in the same month. Oh, it's a dollar game out there in the big world. So if you monitor this and you see how much it fluctuates over time, you might say, okay, I'm going to buy 50 kVAR increments. So what is that? 2, 4, 6, 7. I'm going to buy this. It's going to have 7 50 kVAR increments with automatic switching. So then it has controls that monitors the power factor, and it switches the amount of capacitance in and out of the system so that it sets it between 95 and 1. Yeah. But that costs more. So, you know, if you do it with fewer banks or one big bank, then that $75 might turn out to be $35 or $40 for the project. You know, I mean, there's always more detail you can drill down to. Okay, calculate. So anyway, I said I'm going to buy a 350 bank, 75 per, 26,250. I guess that's installed. And so if you, just to simplify, if you said every month was just like this one, then your savings are 20,328 and your payback's 1.3 years, which, you know, hey, that's better than bank interest for sure. Pretty good project. Okay, so let's calculate, this is the current reduction. And so before correction, we were 882.4 kVA. So that's just 1,000 volts times amps, and those are RMS volts and amps. And so if you divide that out, you get 1,061.4. After correction to 95%, the amps falls to 864.7. So we're saving almost 200 amps, about an 18.5% reduction. Okay, that's all I got on this one. Questions? Okay, well, let me show you. This is actual data from Florum. I'd like to send you all this, but I'm not sure I can. I have to get permission. But anyway, this is what they call interval data. So this is where the utility, come on now, don't do this to me. Well, my phone so far hasn't crapped out completely. How are we doing? I've got, you know, I had 3 bars. I streamed over my phone the first class, and it didn't hiccup once. And I had 3 bars. I've only got 2 bars now, and it's interrupting. I don't know. But this is where the utility company came in and put their recording meters on the entire facility. And so this is 30-minute interval data. And you can see this was 2019. You got the date, you got the time, you got the time split out by itself. So there's the metered KW. I don't know what they intended for this law. That column's all 0. There's your kVAR, and there's your kVA. And I calculated. I guess they gave, you know, when it's calculated, I put it in. But so there's the KW, there's the kVAR, so that's the kVA, and I went ahead and calculated power factor. Okay, so that's kind of interesting. If we go all this, you know, so this is like what, 8760 times 2. So was it? I don't know. It's a whole bunch of data. But if you go to the bottom, and then if I insert a plot, where's the scatter plot? There they are. There you go. Hello. Come on. Don't freeze up on me here, honey. What am I doing? I may have choked my computer. I don't know. Uh-oh. Not responding. This may be one of these courses. I don't know, man. Ah, there we go. I just wanted to make this a little bigger is all I really wanted to do. I don't be doing that. Get that. Golly. Look at that. Not what I'm trying to do. Well, I don't know that I can make it any bigger. Normally I could, but let me try this corner. Oh, that corner is going to work. There we go. That's a little bit bigger. Okay, so you see, this is what you see. I think these guys had some power factor correction going on because this is pretty good. there's not much of a project here because they're pretty big. I mean, they're 5, 6, 7 megawatts. So it's a good size. They make porcelain tile. So it's a big plant up in Clarksville. But you see, what's their low? I don't know what their one little dip, but beyond that, it looks like they hitting 0.92 or something like that. That's not too bad. And, you can look across here, with information like this, I mean, you could divide it up into months and you could see what you thought their billing demand was going to be. And then you could say, well, how much do we think we could really save on this? But I mean, 95 is right in here. So they're spending most of the time right about 95. So it doesn't look like they've got just a whole bunch. That's probably better than most places. If you're not doing correction, it's probably not going to be. This may be when capacitors kicked off or something. That probably is. They probably had a big capacitor bank go down for a short period, and they caught it and they put it back in service. Yeah.
When you get billed, is it based on your lowest or your average?
Lowest average what?
The power factor. If you're saying that they're having.
That's a good question. It's at the time when you set your peak. Well, they actually look at a couple of times, because what usually happens is you'll have your worst leading power factor, which is caused by inductance, when you have your maximum demand. So at whatever time you set that demand, they look at that. And then they also look at the minimum demand, because at minimum demand, you're likely to have a lagging power factor. So then they'll look at that. So you may actually be 2 different times of the year, of the month, that key a demand charge. Oh, they're sneaky little rascals. I mean, they're trying to maximize their income. And, there's justification for this. I'm not trying to get on the utility sector. But anyway, all right, I'm going to delete this before I shut down my whole computer, which would not surprise me at all. Okay, there's that. Okay, now we're going to look at some of these rate structures, if I can find them. I think I can. Let's see. Rate structures. That's in this course, I think. Power rates. Because I emailed you all of these. And if you can't sleep at night, you can get them out and start reading them. And I guarantee you'll be asleep pretty quick. So I'm going to start down here. These are the smallest up to large facility rate structures. There we go. All right. And we'll look over this a little bit. I got to go get a chair. I had a knee replacement back in December, and standing up for an hour and a half, kind of not good on that knee. See, when you get old, your body parts start wearing out. Not exactly what you want to hear, but anyway, I guess it's better than the alternative. I'll try this. I don't usually sit down and do this, but okay. So this is and these are downloaded. You can find, I just went to the NES, National Electric Service website, Google commercial rates and punch around a little bit. You can find a folder that has all of these in them, or a site where you just select them and they just download right to you. So this is a general service agreement. So it's not heavy manufacturing or industrial. There's different rates for those. There's lots of different rates out there. But so this is basically for a customer's contract demand is $5,000 or less. Okay, so or 5,000 kW or less. So 5 megawatts, that's pretty good size. I mean, text load used to be on the order of 5 megawatts on average, but now with these new buildings, I suspect we're probably going to push 8, 9 megawatts, something like that, which, for Cookeville Electric Service, that's pretty big load, What, the hospital is what? I don't know, 4,500, something like that. And I don't know, Fleet Guard's pretty good size. There's a few others around. Okay, and so it's going to be for anybody of any size, it'll be three phase 60 hertz. So basically, okay, so what it's got is it's got rate 1, rate 2, and rate 3. And so rate 1 is up to 50 kW. So, you know, that's pretty small. Now, a big house, not my house, but, you know, some of these big houses, some of these rich guys have, they can push 50 kW or more in load. So that's like a really big, maybe a 7,500, 8,000 square foot house, something like that. I'm just going to I'll do the last one because they tend to get more complex. So let's see, higher customers, let's see. If the customer's currently effective contract demand or its highest billing demand during the last 12-month period is greater than 1,000, then you're going to be on this. Okay, well, so just, you know, think about yourself. You know, you go out of here and you get together with some buddies and you start up a little business and, you know, you got to set up electrical service and you sit down with the guy and he goes, service charge, $934.50 a month per delivery point. That's per meter. Delivery point is a meter. So, you know, if you rented some big place and it had 3 meters, holy crap, I'm paying 3 times this a month and I hadn't bought anything yet. Okay. And this charge just showed up in the last couple of years, the TVA grid access charge. Oh, our friends at TVA want to dig a little deeper into your britches. So, 205.30 per month if the customer's average monthly kilowatt hour usage during the last 12-month period is not more than 150,000. Oh, if it's more than that, then your grid access charge is going to be 579.04. Man, this is getting into some money and I haven't bought anything yet besides access. Okay, demand charge. Summer period. And there's notes below that define, I mean, this is kind of a legal document, so most of the definitions are in here. There may be, the language may be something that you're not used to reading, so you got to think about it a little bit, but the definitions are in here. Okay, so on demand charge, in the summer, the first 1,000 kW billing demand per month, 1980. See, when I said those other rates were a little old, those other rates are probably 10 years old when I made that PowerPoint. So now the first 1,000 are 1980. Excess over 1,000 kW billing demand per month goes up a little bit, 1993. And then if you have an excess, it's 1993 per kW per month for each kW, if any, of the amount by which the customer's billing demand exceeds the higher of 2,500 kW or its contract demand. So most of the time you wouldn't pay that last one because you negotiate your contract demand when you establish service. And so you should have a pretty good idea how much electricity, you know, what equipment you're going to have and what's your peak, what's your maximum. You usually set the contract demand another 10 or 20% above what you really expect to give you some variance there. Because they don't like you to go above your contract demand. Because what the utility does, when the utility plans how much capacity it needs, it looks at all these contract demands. And that's kind of the worst case. Because they figure if they add up all the contract demands, then their actual demand will be less than that because almost nobody gets to their contract demand because they penalize you for it. Okay. Now in the winter, it gets markedly cheaper, right? So the first 1,000 goes from 1980 down to 1884. Well, that's less, not a whole lot less. And so the only thing that changes is the rate numbers. And then the transition months are October, November, and April, May, spring and fall. Because the loads are, you know, the climate's mild. least around Tennessee in those, compared to the winter and the summer. Well, they don't even give you a break here. Sometimes there'll be a little bit less, but so they don't give you a break. Okay, so the energy charge. So for the summer, the first 150,000, it's 5.886 cents. And over that, it goes down. Now notice, demand is what they call progressive. As you use more and more, it gets more expensive. Energy is the other way. It's regressive. It gets cheaper the more you use. Some rates, it gets significantly cheaper, like big, we'll see some of the big rates here in a little bit, okay? But even these get, but so in this rate, on the energy, they're not even changing for the seasons, right? It's the same numbers. Kind of interesting. And there's something, COVID relief credit. Apparently there's a COVID relief, I wasn't aware of that. I had missed that. Shall expire when TVA discontinues the pandemic relief credit on the wholesale invoice. So TVA is doing their part, I guess, help everybody along. That's kind of interesting. I had not seen that before. You didn't know how exciting electric rates could be, did you? Okay, adjustment. The base demand and energy charges shall be increased or decreased in accordance with the current adjustment addendum published by TVA. So I know, I don't see them, I'm not aware that they adjust the demand rates very much, but they do on energy, they publish a fuel cost escalator or fuel cost adjustment. And based on their fuel mix during a particular month, they have a little add-on, it might be 0.0025 per kilowatt hour. It gets added on all of the energy. In fact, that Florum, oh God, I'll try this. So I've come back here on this sheet, and I've done a bunch of programming up here, but here's Florum's rates. And I've got it out here monthly. They've got on-peak and off-peak demand and all kinds of stuff, but there's their fuel cost adjuster at Florum. So that's dollars. So what is that? 1.4, 1.6, 1.6 cents per kilowatt hour that got added in to the total. So that's pretty common. Is this? Yeah, this is the right one. Well, where am I? I'm lost. This the one? Yeah, this is the one. I got too many files open. Okay, so seasonal periods. June, July, August, September is the summer. Winter, December, January, February, March, and the rest are transition months. Determination of demand. Distributor shall meter the demands in kW of all customers. The metered demand for any month shall be the highest average during any 30 consecutive minute period of the month of the load metered in kW. So they got a 30-minute window. The measured demand for any month shall be the higher of the highest average. The measured demand, now let's see, this is metered. Okay, so say, look, the terms are changing. There's metered demand and measured demand. Okay, so the measured demand for any month shall be the higher of the highest average during any 30-minute, consecutive 30-minute period of the month of A, the load metered in kW, so that's the real demand, or 85% of the load in kVA. So see, this rate has an 85% threshold for penalty. So see, that's where, whereas in that example, we took 95% of the kVA, and that's what they got billed for. So you take that number and you compare it to the real, and then you got to pay for the bigger of the two. plus an additional 10% for that part of the load over 5,000 kVA, which is getting up there pretty high in this. So that may or may not kick in. And such measured demand shall be used as the billing demand. So see, we got metered demand, measured demand, and now the rubber meets the road, the billing demand, which is what turns into dollars. Billing demand, except that the billing demand for any month shall in no case be less than 30% of the higher of the currently effective contract demand or the highest billing demand established during the preceding 12 months. So they're going to, okay, and I've seen this kick in. We've been to a few plants. There's one up in East Tennessee, and we get a year's worth of their utility data, and you started looking at their KW billing demand, and it was like 300, 300, 300, 300. And I'm sitting there going, now, look, these guys, they may be consistent, but they can't hit the same flipping number every month. And what it was is that was 30% of their contract demand. So their contract demand, I don't know, they set it, they moved equipment out, they reduced their load, and they had this big contract demand. And so they were pulling 200, 225, but that 30% was 300. And so they were paying on 300 every month. And they didn't know it. We sat there and we said, hey, either you guys are really consistent or this is on your contract demand. And the utility guy was there and he said, yeah, they've got, it was 1,500, whatever the number was. He said, they're paying on that. I said, well, you need to renegotiate this. If you're not going to go back up in demand, then you need to renegotiate this. Because, you can call them in and renegotiate. Of course, they're liable to decrease one thing and increase something else, but anyway, you can certainly try. Okay. Minimum bill. The monthly bill under this rate structure shall not be less than the sum of A, the base service charge and grid excess charge as adjusted. So they're going to take that, they're going to add to it the base demand charge as adjusted, applied to the customer's billing demand, and C, base energy charge. So, and they put this stuff in there to say they've got service at a big plant and say there's a fire and the plant goes down. And it's basically down for 2 months or 3 months. They're not using anything. Well, the utility company is going to get something. So they write in there a way to calculate a minimum bill, and you're going to pay based on that, whether you take anything or not. Seasonal basis. Customers who contract for service on a seasonal basis shall be limited to 2,500 kW and shall pay the above charges as adjusted, plus an additional seasonal use charge equal to 1.33 cents per kilowatt hour per month under one of the base charges. I'm not really familiar with this. Wow. That's interesting. So I don't know. I'm not going to fight my way through all that, but anyway, payment, they want your money, single point of delivery. So anyway, that's pretty good. You can go back and read over that. I will too, but I don't want to fight through it right now. Okay, so let's see. I don't know. We don't want to do all of these. We got a little bit of time left. And then it's time of day. Well, let's look at the big guys, because things change pretty significantly here. I thought that was the big guys. Maybe that's not. Is this? But not more than that's not the one I want. Manufacturing. This is manufacturing rate. Let's see what this. Large manufacturing. There we go. That's pretty good. See what we got here. Greater than 5,000. And you got to be in certain industrial codes. You got to be in a manufacturing SIC code to qualify, because they give the manufacturing people a break on the rates. Let's take a look at this. Base charges adjustment. There's stuff on facility rental in here. Okay, so reactive demand charge. This is the power factor. So this is the way these people are paying for power factor. Now, in the previous rates, what have they done? They've increased the billing KW. Here they don't do that. Here they actually calculate the reactive demand in kVAR and charge you for the kVAR that you use in excess of what you're allowed based on the power factor in your KW, okay? So if the reactive demand, whatever the kVAR that you use that month, is lagging, which most of the time it is, at least during the peaks, during the 30 consecutive minute period beginning or ending on a clock hour of the month in which the customer's highest metered demand occurs. So see, they're chaining this one to the highest metered demand. There shall be added the customer's bill a reactive charge of $1.46 a kVAR in the amount, if any, by which the reactive demand exceeds 33% of the metered demand. Okay, so if you make yourself up an example, say, take a demand of 10,000 or 1,000 or whatever, and if you figure the kVAR that you can have for a 95% power factor, and then take 0.33 times whatever the KW you assumed, you get the same number. So basically this 0.33, you have to go through some calculations to see it, is basically saying that the threshold is 95%. The math turns out to be the same. Say these guys, they got all kinds of ways of saying this. And when you don't do this all the time, you go read a different rate structure and you start, what are they doing? Just give me what I'm used to, But if you go around the country, you have no idea. I mean, this is tame. Some people are paying real-time pricing. Some utilities will pick 3 or 4 particular hours per year and base charges on your power factor on those 3 particular hours during the month. I mean, there's crazy stuff out there. So, if you go to work in the Tennessee Valley, TVA as a generator, you're going to see this kind of stuff. If you go to work in California or New York or Canada, good luck. At least you have some idea what the terms are, but you're going to have to dig in and read the rate structures and then probably get somebody to explain them to you. Because, I mean, I've over the past umpteen years, I've been around the country and around, and some of the times you just go, what in the world are these people doing? This is the craziest thing I've ever seen, but it's out there. Okay, so that's what that 33%. So if you take 33.33 times the metered demand, that is the allowable KW for a 95% power factor. And you should make a little power triangle and convince yourself of that. Well, we could go back to that example. What was that? It was, okay. Do I have my calculator? No. Is it in there? Because it was, what was it? It was the KW was 683, was 683, wasn't it? And the allowable was 224, okay? So hope this works. 83, 225. So basically, yeah, they've rounded it. They just take 0.33. If you want to get it exact, you got to take some more digits. But what is it? It was 224 something. 224, say 0.5 divided by 683. Yeah, this comes out like 0.3286, something like that. That's pretty close. Okay. So if the reactive demand in kVAR is leading during the 30 consecutive minute period beginning or ending on a clock hour of the month in which the customer's lowest meter demand, excluding any such meter demand which are less than 25%. God, there's so many little caveats in here occurs. Then, and say, so leading helps the utility because 90% of their customers are lagging. So if they got a customer lead, it helps them. And so for that, for doing them that favor, they only penalize you $1.14 for each leading, but there is no allowance. You pay for all of them. You see, so on the lagging, you get 0.33 times the meter demand is allowed, and you pay for those beyond that. On the leading, you pay for all of them, but instead of $1.46, you pay $1.14. Interesting world we live in, seasonal periods. I know you guys are getting tired of this. I don't blame you, I am too. All right, so I guess we've got three different B, C, and D. Let me see, this will be for different size services. I'm not sure, where does it say? Where does it say? MSB, well, I'm not sure. That's what I thought that was. They say jurisdiction shall require contracts for all service provided under these rate structures. The contract for Schedule MSP and Schedule MC customers shall be for an initial term of at least 5 years. I think they're different. I think they're different sizes. On peak. Huh. Not sure where that. Yeah, here it is. Okay. MSB customers with contract demand greater than 5,000 but less than 15,000. C is 15 to 25, and D is over 25,000 or 25 megawatts. 25 megawatts get to be a pretty good size load. If you get much bigger than that, you're going to be direct serve and you're going to negotiate your own contract. Okay. So there you go. Service charge, admin charge per meter. On peak, oh, look, the numbers are better. Pretty much the same. Okay, so they're going to have an on-peak time and an off-peak time. On-peak, the on-peak will be 6 hours, and it will be adjusted differently in the summer and the winter. It's the 6 hours that they expect to have the grid to peak. So let's see if we can find that description, contract, minimum bill, determination on peak, off peak periods. Where are they giving the months? I'm sorry, Cloud. On peak. Well, it'll say which. Oh, well, that's right. Yeah, this is time of day. Does it give the times? That's minimum. That's minimum bill calculation right there. Determination on peak, off peak, maximum. Rate structure. On peak should be. Ah, there it is. Okay, and catch this. I know not the justification for this. Well, I understand some of it, except for Saturdays, Sundays, and November 1st. What's special about November 1st? I have no earthly idea. And the weekdays that are observed as federal holidays of New Year's Day, Memorial Day, Independence Day, Labor Day, Thanksgiving, and Christmas, on peak hours for each day shall, for the purposes of each structure, be 1 p.m. to 7 p.m. during the months of April, May, June, July, August, September, and October. So see, that's during the cooling season. And during the heating season, at 4 a.m. to 10 a.m. during the months of January, February, March, November, and December. So those are the hours that are considered on peak and off peak. Okay. So your on peak demand. So these meters, they calculate an on peak demand during whatever hours is on peak and an off peak demand. And the maximum is the larger of those two. So you could set your biggest could be on peak or it could be off peak. Okay. So on peak demand, you're going to pay $10.24 for, and then whichever one is biggest, you're going to pay an additional $2.43 for on demand. And then excess, if you like exceed contract or stuff like that, you're going to pay for that separately, but that doesn't usually come up. And so you see, then we've got summer period, winter period, and transition. And it's pretty common. Transition and winter oftentimes are the same. Summer's a little bit, but they're not tremendously higher. So that's your demand charge. Okay, schedule, so the different rates. So on peak hours is pretty simple. One rate, you got on peak energy, you got one rate, multiply it together, just like a little example, that's your on peak energy charge. And then you get to the off peak block. And this is another convoluted mess, okay? So what you do, make sure I get this right. I think it's the on-peak demand. We'll check this, but let's assume that's right. So you take your on-peak demand times 200 hours. And so that's kW times hours is kilowatt hours. So that gives an amount of energy, and that's called your block one energy. And then you pay for it at the block one rate, okay? Now, you only have to pay for what you use. You know, so every time you do one of these calculations, you got to make sure that, well, that's not more than I use, because you only have to pay for what you use. But most of the time, you get all the way down into block 3 or so, okay? So then you take the same demand times the same 200, and that gives the same result. And so long as you've used all of that, then you pay for that during the block, for the block 2 rate. And you see, it's getting significantly cheaper, okay? And then you take that same demand, there it says right there, metered on peak demand. And then most of the time you don't have to use, if you multiply that by 400, because see that's 400, that's 200, 200, 400, 800, that's probably more than you would have used. So generally speaking, you saturate these two blocks and then you pay for the rest of them at this rate, okay? Minimum. Minimum off-peak energy per month shall be applied to any portion if any of the minimum off-peak energy takings amount that is greater than the metered energy. What? I don't know what that says. The minimum energy take. I don't know what that means. Anyway, so we go through this for just depending on which month we're in. Summer, winter, transition period. So, you know, if you just look at this, you can save some money. For example, at Florham, they had some big ball mills like 900 kW ball mills. And they were running them on peak. And their production was not full. If they were full production, they'd run them all the time. But they had the opportunity to schedule those off peak. So 900 kW, you know, there are some demand savings, but, well, yeah, because if you move, let's see, well, this is, where's our demand? You know, so if you're on peak, you're 10 bucks. And if this goes to off peak, you only pay $2.43. So that's like $7.50 or something times 900 a month. And then the energy, you know, like if you're in the summer, if that energy you were paying 7.35, 348, and you could drop, and if it would fall to this third block, oh my goodness, you could pay 1.6. So say if you can schedule, and that's why they do this. They want to give industry, large manufacturers, enough incentive to save money on their utility bill to do their best to move these loads to the off-peak period. That helps the utility like crazy. So they offer this to them. Okay? That's pretty much it. Looks like a great homework problem, doesn't it? There might be one in your future. I'd say this would be a good rate to exercise. Now, I'm going to shut up here in a minute. I'm about to get hoarse. But so this is this forum thing again, which I'm bound, darned and determined I'm going to crash my computer. But the point of this spreadsheet was to investigate putting in some micro turbines. So what I can do, this is the C8 combined heat and power tab. And so I can put in a number of kW here, and it starts with their last 12 months bill, and then it recalculates their bill based on their rate structure if they had had a certain amount of generation in place. So, and what's interesting here, when you get down, this is their recalculated bill. For example, you see all these 3100s, 3100, 3100, 3100, 3100, 3100. That's an off-peak demand. What that is that's their minimum bill showing up. Because if you go, so, you know, this refers back over here where I have all of these demands. So I have the 30-minute demand information. And so if I put 5,000 kW of generation, then that's 5,000 that they generate on site. They don't buy from the utility company. So that comes off of their purchases. Okay. But when you get into their rate structure, they calculate that minimum bill. And when I put in 5,000 kW, all of a sudden, I'm getting caught by the minimum. Now, I've not calculated here how much. I could do that. I probably should have put a column in here to say how much, because I'm going to pay for 3,100, even though, you know, maybe I only needed 2,500. Because, you know, when I take that 5,000 that I'm generating and subtract it from, you know, what was needed that month, all of a sudden, that may be, I've got another sheet up. I haven't looked at this in a little while. I've got another sheet up, what is this? This is, we were looking up here, the months, kilowatt hours, cogen kilowatt hours, purchase kilowatt hours, on-peak energy use kilowatt hours, on-peak kilowatt hours generated, on-peak kilowatt hours purchased. So you can kind of see missed on-peak generation. So anyway, I'll review this and we'll look over it some more. But I mean, it is kind of, it's a little bit interesting if you go back up here and say you put in 2,000, then all of a sudden, see how those 3,100s go away. because you're only generating 2,000. And so you still have, you can see what their peaks are. They're off peak and they're on peak. So then you go back and look at the financing of it. It was, say it's still 7-8 year payback, not just a great payback. But the other thing it did, it reduced their emissions. Yeah, TVA carbon factor for 2019 for across the Tennessee Valley, that's pounds of CO2 per megawatt hour. So the TVA published number is 741.66. So on average, you know, I mean, they got some solar, they got their wind is nothing, but then they got some coal, they got some nuclear. Their fleet average is about 742 pounds of carbon CO2 equivalent emitted per megawatt hour. And then let's see, electric carbon metric tons per year. So you can see what they were doing, what the company was doing, what it would go down to, purchase electricity, carbon saved, but then we got to burn more natural gas on site. So anyway, overall net decrease. So they were going to save 1,570 metric tons per year of carbon. And the company was very interested. These companies that sell in international markets and things like that, those customers want to know that. They want to know how much carbon they're putting up, for sure. It's getting to be more and more important in industry all the time. Okay, I think I'm going to stop there, and appreciate your kind attention. I'm glad we maybe have made it through unscathed. God bless Verizon. And maybe TTU IT will come and give us some better equipment next week, sometime soon. I hope so. Thanks, everybody. Have a great day. Be looking for emails from me.